Welcome to section 3 of calorimetry, section 3. So in the last videos we learned about what is the amount of energy that I have to give for mass m to increase the temperature by delta T. For this we need to know what we define as a specific heat capacity. So if you know the specific heat capacity, then you can tell how much energy you need to give to increase the temperature of, say, 5 kg copper from 5 degrees to 200 degrees. So you need to know specific heat capacity. But how to find the specific heat capacity? How to find C? This is done by calorimetry. Okay, this is done by calorimetry. Now, what is the principle of calorimetry? Now, imagine you have substance A. So the substance A, and then let's say this is Ma, and then specific heat capacity is Ca, and then substance B, Mb and Cb. Let's say you heat this to temperature T1, Ta, and then you heat this to Tb. Let's say your Ta is greater than Tb, right? And then let's say, so let's go one by one. So one is take two substance, two is measure Ma, Mb, third is heat and measure Ta, Tb. Then the fourth one is mix A and B, measure T result. Okay, so what is the heat lost by A? Is Ma, Ca, T A minus Tr, right? Tr. Now, what is the heat gained by B? Mb, Cb, Tr minus Tb, right? The reason is, as I mix this both, the resultant temperature would be in between Ta and Tb, so it's Tr minus Tb. So the by principle of calorimetry, delta Q lost by A is equal to delta Q gained by B. So let's do this once again. Delta Q lost by A is equal to delta Q gained by B. So, and this one was Ma, Ca, Ta minus Tr is equal to Mb, CB TR minus TB. Now this is principle of calorimetry. By principle of calorimetry, these both are equal. And with this equation, let's assume that you know obviously you know MA and MB. Let's assume that you know CA, and you know, because you measure TA and T result, you know T result and TB. So if you know all these stuff, then you can find CB. So if you know the specific heat capacity of one of the body or substance, then you can use that to find the specific heat capacity of an unknown substance. So that's how you use a principle of calorimetry to find the specific heat capacity. Now let's take specific examples. So in this particular example, I can take water, right, and this can be A, and then I can take oil, and this can be B. So I know that for water, Ca is equal to 4.2 kilojoules per kilogram degrees Celsius. Then I don't need to put this. So I know that it is 4.2 kilojoules. So then I need to find what is the specific heat capacity of the oil. That's how you use the principle of calorimetry. So how does a calorimetry look like? And you can see for good representation in your textbook, but then there are certain key aspects. So first, you have, it approximately looks like this. So inside is, now this is copper. This is copper, and then I put wool. Now why do we make this construction? So this is typically wool. So wool has a very high specific heat capacity, is extremely high. What that means is that it's a very good insulator, right? It's a very good insulator. Copper has very low specific heat of capacity. It implies that it's going to be if let's say you put water inside this. So if water gets 4,000 joules and it increases temperature by 1 degrees, then copper has much lower specific heat capacity than water. So it's going to absorb all that heat very easily, and it's going to increase its temperature very easily without much resistance, right? So that's the whole objective of having a very low specific heat capacity, so it won't affect my measurements, what I need to do. And then above this I have the thermometer, and then I have a stirrer. I'm very bad in drawings. I hang this thermometer in a stand, right? So this is in short a calorimeter, right? The key to remember is that there is some amount of heat that this calorimeter absorbs but then that heat is much lesser. So when I mix, so let's say this is liquid A and I mix some liquid B into this, the heat absorbed by this liquid A would be much higher than the heat absorbed by the copper to get into the same temperature, right? The reason is because copper has such low specific heat capacity. Now, that's the whole idea. But nevertheless, there is a certain amount of heat absorbed by calorimeter. So let's say you mix some this liquid is B. So then I heat liquid A and then I mix it, right? So heat lost by A is equal to heat gained by B plus heat gained by calorimeter. So this is very important important aspects that you need to remember is the calorimeter also gains or loses some heat. So with this, let's see how you can find the specific heat capacity of let's say a solid. So let's assume that you have a solid, and you know, this is my calorimeter, and I filled it with I have some solid, and the mass of the calorimeter is mc, the specific heat capacity is cc, the liquid inside is, let's say, water, so it's mw, cw is the specific heat capacity of water. Now both of these is, let's say, initially in temperature T1. So I take the solid and let the mass of the solid be ms and the specific heat capacity be cs. Let this be in temperature T2, and I drop the solid into this liquid. So, and then I find you know, what is the T result. So now I can find the heat lost by solid is equal to delta Q by water plus delta Q by calorimeter, and both of these are gain. All right. So this is equal to MW CW T result minus T1 plus M calorimeter CC T result minus T1. This is equal to delta Q loss by solid, which is T2 minus T result into M solid into C solid, right? So this is all you need to remember. So the textbook has a little bit convoluted, and it's kind of a little confusing, but as long as you understand the principle, I think you're good. Now exactly the same way you can find a specific heat capacity of a liquid. So that you can refer to the textbook, you know, section 11.7 on how to do that. Apart from this, I also suggest you to read section 11.8 and 11.9 by yourself. So that covers the first part of calorimetry. Good luck.